Hello guys, in today's video we're going to see some properties of separable spaces and their relationship with dual spaces. We start with the lemma. It says that let X be a norm space and it has a separable dual space X star. And the implication is that X itself is separable. That's what the lemma says. In order to prove this, we need a certain understanding of closed subsets of separable spaces. So we have a norm space X and M is a subset of the norm space. Remember, I did not say subspace, I said subset. So the subset of a norm space being separable, it means that there is a sequence in M such that the closure of that sequence is equal to M. So the closure of that sequence is equal to the subset itself. There is a theorem. So the theorem says that if X is separable and M is closed, the subset is closed, then it implies that M is also separable. Now, in order to prove this lemma, we need this theorem that if you have a separable space and you have a closed subset, then that subset is also separable. Since X star is separable, there is a dense countable subset on the unit circle such that norm of t is equals to 1 in X star. So now we have, let's consider this as my space X star. Now the theorem says that since X star is separable, so we know from the previous theorem here that closed subset of a separable space are themselves separable. So if I consider the unit circle, that's a closed subset. So this itself is separable, which implies there is a dense countable subset of the unit circle. As we saw here, so M is the unit circle. Now our norm space X star in this case is separable, means a closed subset is itself separable, which means there is a sequence in M, which in our case is the unit circle, and the sequence is Tn, such that the closure of that sequence is the unit circle itself. So therefore we see this line that since X star is separable, so the unit circle is separable, so there exists a sequence on the unit circle whose closure is all of the unit circle. That's what it says. Now we see that the norm of Tn is defined via this formula, and it's the usual soup norm. And now the theorem says that it follows from this that there exists an xn with norm of xn equals to 1 and norm of Tn xn greater than or equal to half. So what's happening here is, so once I have those Tn's, once I have these Tn's, from these Tn's I get the corresponding xn's in my space capital X. So the flow started like I had a separable space X star, then I took a closed subspace or a closed subset which is unit circle, and I showed that there is a dense countable subset of the unit circle, which means that the closure of this thing is the unit circle itself. Now in the next case, once I did that, I got norm of Tn is equals to the soup norm of Tnx, norm of x equals to 1, and from this I got xn. So now he says that it follows from this that there exists an xn with norm xn equals to 1 and Tn xn greater than or equal to half. This is because, well, if the supremum is 1, then Tn xn can be greater than half. Why not? And now we show that if I take all such xn's, then the span is dense in X. Now, in order to understand this, I need you to look at this theorem, which says that there exists a sequence xn in X. Well, the theorem essentially says that there exists a sequence xn in X such that the closure of the span is equal to the space itself, then my space X is separable. This is a theorem that we'll make use of to prove that X is separable. So in the previous case, we saw that what it meant for a subset of a norm space to be separable. And now we see that there is this another theorem which shows that a space is separable if there exists a sequence xn in X such that the closure of the span of the sequence is equals to the whole space itself. So if I can take a sequence in my space X and I can show that the closure of the span is equals to the whole of X, then I can say that X is separable. So let's follow the storyline again. Started with X star being separable. So I said that a closed subspace is also separable, which implies that the set of points Tn on the unit circle are dense in it. Now, if that's the case, then the norm of any of this Tn would be given by the sup norm, the usual formula, such that norm of X is equals to 1. And from here I got a xn belonging to capital X such that this formula can hold. And norm of xn is equals to 1. And I say that since the sup is 1, then for some element xn, the norm of Tn xn has to be greater than equal to half. And what I need to show now that if I take a sequence xn and if I take the span of that sequence and then I take the closure of it, then that should be equal to the whole space itself. So y is given like this, so this is y, and I want to prove that closure of y is equal to X. If I can prove that, then I can show that my space X is separable, and that is what I wanted in the first place. So I had a separable dual space X star, and my goal was to show that X is separable. So now we prove this with contradiction. We say that suppose y closure is not equal to X, so that there exists a X belonging to X complement y closure. This is from the corollary of Hahn Banach, and hence there exists a T belonging to X star. So this T is in the dual space of X, and T annihilates y, and T of X is not equal to 0. So this is simply from the corollary we saw above. And without loss of generality, we can assume norm of T is equals to 1. And now, since Tm was dense on the unit circle, and since T is an element of the unit circle, I can approximate T with Tm to an arbitrary degree of precision that I want. And here I take that epsilon equal to 1 by 4. And we see that this leads to contradiction. We see that, so from here we saw that Tm(xm) is greater than equal to half. And then I just add minus Tm. So since xm is an element of y and T belonging to, and since T annihilates y, so T of xm would be equal to 0. And then I can write it as norm of Tm minus T, norm of xm. And this is equals to 1, we saw here, and this was 1 by 4. So from here we see that half is less than 1 by 4, which is a contradiction. So indeed, my space X is separable. Just a very last things before we wrap up our chapter on Hahn-Banach theorem. We would just see the statements of two theorems, which are the separation theorems, without going into the proofs of them. So the first Hahn-Banach separation theorem says that let U1 and U2 be non-empty convex and disjoint subsets of a real norm space X. And suppose that U1 is open, then there exists a functional in X star and gamma belonging to real numbers such that f of u1 is less than gamma and f of u2 is greater than equal to gamma, where u2 is not necessarily open and u1 is open. If I have two non-empty convex disjoint subsets, then a functional belonging to X star can separate them. So this is the first Hahn-Banach separation theorem. And the second Hahn-Banach separation theorem is even stronger. Here it says that let u1 and u2 be non-empty closed convex disjoint subsets. And there's a real norm space X, and suppose that u1 is compact now. Now this one is compact. Now there exists an f belonging to X star and gamma belonging to the space of real numbers, and epsilon greater than 0 such that this thing is satisfies. This inequality holds, or this statement holds. So this is even a stronger statement or theorem than before, because now it creates sort of like a gully between these two non-empty closed convex and disjoint subsets. And finally, we see Helly's theorem. We see that let X be a norm space and T1 to Tk be bounded linear functionals on X, and let C1 to Ck be scalars. Now the following statements are equivalent. Now it says that there exists an X star in X such that T1 X star is equals to C1, T2 X star is equals to C2, and so on. And in order for this to hold, there exists an m greater than 0 with the property that this inequality holds for all scalars alpha 1 to alpha k. Furthermore, if 2 holds, then for any epsilon greater than 0, we can choose an X star and 1 such that norm of X star is less than m plus epsilon. So now we jump to the final section of this chapter. And I'm going to talk about basically two things. The first thing I'm going to talk about is that if I have f as my linear transformation, it maps convex sets to convex sets. So let me like convex sets, convex to convex, where f be a linear transformation. The next thing I'm going to talk about is, that's all I'm going to talk about. The proof is absolutely trivial. I take u to be a convex, then f of u is convex. It follows from this fact that this belongs in u, and hence then this belongs in f of u, and hence it's convex. Now let X be a real norm space and f from X to R be a non-trivial linear transformation. If u belonging to X is open, then f of u is also open. Now this is my claim. This is what I'm saying, that it maps open sets to open sets if f be my linear transformation. Now I start with fy in the image, and then I jump back with y in u. So I trace it back what y it was, and since my u was open, then there exists a ball around that y. Now since my f is non-trivial, I can choose an x which is not in the kernel of f with norm of x is equals to 1, and I find that this quantity, it belongs in u for alpha being in minus epsilon to epsilon. And then the next thing that I have is I take f around it. So if I put a f around this, I see that, okay, it's an open interval with middle point being f of y. Now I see that f of y lies in the interior of f of u. But since f of y was any point in f of u, so every point is an interior point of f of u. And thus, f of u is also an open set. So this brings us to the end of the chapter on Hahn-Banach theorem. And I wish to start with reflexivity in the next chapter. See you in the next video.